Hello, all, and welcome to Artham Academy, aspiring leaders in innovation and technology. In today's video, we will talk about Brayton cycle. Brayton cycle is a very important cycle that is used in the power plants. Brayton cycle is also known as gas power cycle. In this video, we will talk about in detail about the Brayton cycle, the processes that are there in the cycle, also about its application, and also the ways of improving it. So stay tuned for getting informed.
Brayton cycle. This cycle is very common and is named after George Brayton. This cycle is used in the gas power plants, same as the Rankine cycle is used in the steam power plants, where the working fluid is steam and the working fluid is gas. And basically there are two types, open and closed. The Brayton cycle is the basis of the conventional gas turbines. And this is how the normal Brayton cycle looks like. It has a compressor, a combustion chamber, a turbine, and an heat exchanger through which the heat is rejected outside. So let's look how the TS and the PV diagram looks like and what are the ideal processes that are assumed in the Brayton cycle. This is the PV diagram and the TS diagram. Here you can see the process 1 to 2. It is reversible adiabatic compression. And in the PV diagram, it's quite evident that from 1 to 2, the volume is being reduced, that is, the compression is happening. While you can see the same 1 to 2 process in the TS diagram, that the entropy is same because it's an irreversible adiabatic process, but the temperature is increasing. And here we can conclude that during the compression, the temperature increases. Now if we move from 2 to 3 in the PV diagram, here you can see that in the PV diagram, if we move from 2 to 3, there is a Q input. That is, this is the combustion chamber, constant pressure heat addition. But the pressure remains same. But when we look at the temperature, from 2 to 3, the temperature increases a lot because we are putting a lot amount of heat here. After that, 3 to 4, there is expansion process that's happening, and that we can see the volume has increased from 3 to 4, but the pressure has decreased. And same during the compression, during the expansion process, the temperature decreases and it comes down. Finally, from 4 to 1, there is the heat exchanger that is used to remove the heat. And that's why the temperature is finally decreasing and coming back to its original position. And that's constant pressure heat rejection. On various derivations and calculations, we have got to know that efficiency depends upon the pressure ratio and the type of the gas. The pressure ratio, here we can see that in the PV diagram, the P1 pressure, the initial pressure, and the P2 pressure. So P2 by P1 is the pressure ratio, and gamma is the nature of the gas, whether it's a diatomic gas, polyatomic gas, and whatnot. So this is the brief overview of the Brayton cycle as well as the cyclic processes that are happening. Let's dive more about the open and the closed cycle. Open and the closed cycle depends on the working conditions of an area through which the operation has been happening. But usually closed cycles are used because they are more sophisticated and control is easily available there. But let's have a brief discussion about them. So in the open, there would be a constant fresh air input or fresh gas input from the outside. But in the closed cycle, a constant gas would be running cyclically and that the transformation would be happening. But in the open, you take a fresh air from outside and you reject. You do not recirculate that same air. Let's look at some of the comparison. Because of this process, open cycle generally has low thermal efficiency, whereas the closed cycle has high thermal efficiency. In open cycle, the erosion problem is generally high because air of different moisture level enters the system, and that can corrode and that can cause a lot of problems to a lot of expensive items in the gas turbines. That's why erosion is generally high in the open cycles. Whereas in closed, there's no outside input That's why we do not care much about the erosion there. Wait, open system is not that much sophisticated, but in the closed system, in order to circulate and in order to make that cycle happen again and again, you have to carry a lot of sophisticated items. That makes the system heavy, generally. The application of the open cycle includes aircraft, stationary, power plants, and automobiles, whereas for the closed, it's our ships and submarines. Now, before moving forward, let's look at some of the assumptions because those are very important and create a boundary through which we can operate and use the formulas that are derived. So, air is the working substance. We are using air as the fluid in this cycle. Specific heat values remain constant. For example, we are moving through different temperature, and in real life, specific values generally change with temperature. But for the ease and for the derivation, we have taken specific heat values as constant. Change in kinetic and potential energies are negligible. Obviously, we cannot have that component, otherwise it will increase the complexity of the equations very much. No loss of pressure while flow through the components. In real life, it happens from one part of the component to other part of the component. Generally, the loss of pressure happens. But this is an ideal scenario. That's why we are taking that there is no loss of pressure. No heat loss in compression and expansion process. Generally, the process is assumed to be adiabatic, but there is nothing adiabatic completely. There is obviously some loss of energy, and that's why, for ease of our doing the problem, we have taken this as no heat loss in compression and expansion process. The relation for the thermal efficiency of a Brayton cycle depends upon the pressure ratio and the nature of the gas. This we have already seen, and this is the graph that shows it, that with the efficiency, that with the nature of the gas, that's the gamma value, the efficiency also increases, and with the pressure ratio, with the increase in the pressure ratio also, the efficiency value increases. This is a general graph. It will give you an idea about the efficiency and the pressure ratio relation. Now we have talked about the general Brayton cycle, that it has normal processes. But in order to increase our work output and to reduce the effort or the work we are putting in the cycle, we have to do certain amount of steps, and those are regeneration, intercooling, and reheating. In real life process, if you go to any power plant, you would mostly not see the Brayton cycle that I explained you earlier. It will obviously be a modified, because in the real scenario you need maximum output, and these are the three processes that are generally followed in the real life power plants, because it either increase the efficiency or increase the work output, which makes Brayton cycle useful. So let's talk one by one and go to regeneration. So regeneration. In regeneration, it means that the exhaust gas is having a lot of energy sometimes. So why not use that energy in heating the fluid? So as soon as the fluid after getting compressed comes out, we can supply that amount of energy to that fluid so that we have to give less amount of energy in the combustion chamber. And this is the whole concept of regeneration. Heat addition decreases in the combustion chamber. Efficiency increases with less amount of heat, and both heat supply and heat rejection decreases. It quietly makes sense. Now you can see in the graph that this is the original cycle and this is the regenerative cycle. So there is a quite lot of difference if we use the exhaust gas. Intercooling. In intercooling, we can generally say that the idea behind is that isothermal work is very less as compared to the adiabatic work. And using the intercooler, we are somewhat trying to make that process isothermal. Because if we see this in the graph here, if we remove this red part and if we try to calculate the flow work on the p-axis, because the flow work is calculated on the p-axis, this will be a lot of work. that we will be giving through compressor. But if using the intercooler we take this path, this red portion amount of work we don't have to give it again. And this is how the adiabatic work becomes less and we somewhat become close to isothermal work. And that is how we are giving less amount of work in the compressor and we are saving our energy. And this helps us to increase our work output. So this is the whole concept why we are doing it. So if we have infinite number of intercoolers, we will approach the isothermal work. But that's not physically possible. We generally use 2 to 3 intercoolers in the power plants and increase our work output using that. Okay, so both heat supplied and heat rejected increases. The mean temperature of the heat addition and heat rejection decreases. For the same output, the power plant becomes more compact. That is quite understandable. And the efficiency of the cycle decreases. This is because we have to give more amount of heat now. From 4 to 5, we have to give more amount of heat. And the work output increases, but generally it falls in the region where the efficiency decreases. With this, scope of regeneration also increases as the compressor outlet temperature decreases. It means that the compressor output will be as small as possible. We will have more cases of regeneration. So we can definitely form a combination between regeneration and intercooling and can increase the efficiency as well as the work output. Now reheat. This is the last process that we do in the Brayton cycle. The main idea behind is that more heat is added, so more work output would come. And that is, heat is added to increase the output of the Brayton cycle. That we can see that in the process, that extra heat addition is taking place. Okay, the net work output is increased by increasing the work done by the turbine. The turbine output increases. Both heat supplied and heat rejected increases. That is quite evident that from 2 to 3, if we could see here, and from this process to this process, the heat addition increases. And also the heat rejection from 5 to 1, that is also increases. So both heat addition and heat rejection increases. Both the mean temperature of the heat addition and heat rejection increases. That we can say. Because from the process 2 to 3, our mean would be at some this place. But because of this more heat, it would come little above. Okay. While in the rejection process, we can see 5 to 1. If this process would not have been there, this process would have been here. So the mean would have been somewhere here. But because of this, the mean has increased a little bit. Cycle efficiency decreases in this case also because we have to give extra heat, and that increases the denominator, and that's because cycle efficiency decreases. Scope of the regeneration here also increases because the turbine exit temperature increases this time. So you get it? In intercooling, the scope was there because the outside temperature, we were decreasing the compressor outlet temperature. Here we are increasing the turbine exit temperature, and that's why whenever there is a large difference between the exit and the coming out of the compressor output, that's the scope where we can employ the regeneration technique. So let's look at some of the conclusions. What are the final conclusions that we can see? In regeneration, the work net becomes constant but efficiency increases. Whereas in reheat, the work net increases but efficiency decreases. In intercooling, same thing happens. Increase in work net happens and efficiency decreases. Regeneration plus reheat, when they are combined, now the combination increases the work net and increases the efficiency as well. Reheat plus intercooling increases the work net and decreases the efficiency. Regeneration plus intercooling increases both work net and efficiency. And when we combine all three, it generally increases the efficiency as well as the work net. This is the actual general ideal process that is happening in the power plants, the gas power plants that we see. And you can see that this graph employs everything. You can see the regeneration concept here, you can see the intercooling concept here, you can see the reheat concept here. So everything is employed here, and that is how you optimize it to make your cycle more and more effective. Final note, intercooling and reheating always decreases thermal efficiency unless they are accompanied by regeneration.
That's all for today. We hope that you would have loved the video. For any information, you can contact these below details about our courses and about any information that you need. Thank you.